Hello everyone, my name is Bharat Dau and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. I welcome you all to this 8th lecture of structure of atom. So in the previous class, what we have seen? We have seen that there are two kinds of atomic spectra. One is the absorption spectra, another is the emission spectra. We studied about how both of these are calculated, and we also studied that both of these are complementary to each other. That is, if we study the information conveyed by either one of them is the same, then further we studied the emission spectra of hydrogen atom, and then we established that the lines which we observe in the spectrum of hydrogen atom, we defined it or categorized it into five series of lines. These are Lyman series, Balmer series, Paschen series, Brackett series, and Fund series. We also saw about the Red-Bunk equation, right? And we saw the three variants of this equation. One for the pure hydrogen atom, for Balmer series, then we generalized it for hydrogen atom to any series, and the last one, which is the most general one, we found out by we established that for hydrogen like species, right? Like lithium plus helium plus two, like these ions. Then we solved some examples, and at the end we established sort of touched the drawbacks of Rutherford models and a need for a new model for atom, there we concluded saying that this new model is the Bose model given by Niels Bohr. Right. So in this class, we are going to study about in detail about these drawbacks, and then we are going to study the Bohr's model of atom. Right. Let me write down lecture 7, structure of atom. The first topic which we are going to study is drawbacks of Rutherford model. So according to Rutherford model, an atom consists of a heavy positively charged nucleus surrounded by negative charged electrons, right? Moving around. So according to Rutherford, as a recap, so according to Rutherford, what we had is this is the nucleus and electrons are revolving around it. Let's say these are the electrons. This is the nucleus, and electrons are revolving around it in the form of these circles, right? Let me write this down. The different color. These are electrons, right? And these are nucleus. And according to that, it is revolving. This is the nucleus, right? So accordingly, in this model, the electrons were revolving around the nucleus in this direction, right? So according to the first model, an atom consists of a heavy charged nucleus. So this is the heavy charged nucleus surrounded by negatively charged electrons moving around in a circular path called as orbit. So this is called as orbit, right? This model was analogous to the solar system, right? Where the nucleus may be compared to the sun and the electrons to the planets. The Coulombic force between the nucleus and the electron is, right? The Coulombic force between electrons and nucleons is, let's say, electrostatic force. Let me write this down with a different color, right? The force between nucleus and electron, that is the electrostatic force is K Q1 Q2 by R square, where Q1 Q2 are the charges and R is the distance of separation between the molecules and the electrons, and K is the proportionality constant. So this is similar to the gravitational force acting between the planet and sun, which is G into M1 M2 by R square, where G is the gravitational constant and uh, G is the gravitational constant, M1 M2 are the mass of the species, and R is the distance of separation between the planets and the sun. However, there is an important difference between the solar system and the nuclear model, right? The electrons have extremely small mass and are negatively charged, whereas planets are massive and neutral. The planets revolve around the sun in well-defined circular path, right? However, there arises a difficulty with Rutherford's model. It failed in the light of electromagnetic principle, right? So what we can write is, so we will discuss it. Right? Rutherford's model failed in the light of electromagnetic radiations, electromagnetic principles, right? So we will study about it. It was shown by Maxwell that a charged body moving under the influence of attractive forces loses energy continuously in the form of electromagnetic radiation, right? Thus, unlike a planet, the electron is a charged. Thus, unlike a planet, the electron is a charged body and it should emit radiations while revolving around the nucleus. As a result of this, the electron should lose energy at every turn and move closer and closer to the nucleus, right? So let me write this down and then we will discuss about it. So what Maxwell showed? Maxwell showed that when a charged particle is moving under the influence of other charged particle, the certain amount of radiation has to be emitted, because of which the energy of that particle has to decrease, right? Or radiation has to decrease, right? So what we can write, it was shown by Clerk Maxwell that a charged body moving under the influence of attractive forces loses energy continuously in the form of electromagnetic radiation. Thus, what we can assume this is, what we can conclude from this is, the electrons is a charged body and it should emit radiations, right, while revolving around the nucleus. While revolving around the nucleus. As a result of this, what should happen is the electron should collide onto the nucleus, right? So I will show you the picture. As a result of this, the electron should lose energy at every turn and move closer and closer to the nucleus, right? Following a spiral path. Right? So it should be like this. Right? So electrons, as per this theory, both electron is a negatively charged particle, whereas nucleus is positively charged because of the presence of protons, right? So this is so electron is under the influence of attractive forces, right? Because we know unlike charges attract each other, right? So as per Clerk Maxwell, what he showed, when this electron is under the influence of attractive force, this electron should not have this electron should radiate emission, and we know that energy is nothing but h nu by lambda, that is hc by lambda or h nu, right? Energy is h into nu, which is hc by lambda. As this energy is associated with the frequency, losing the energy should result in losing of frequency, right? Decreasing frequency. So hence, because the radiations are being emitted, so those radiations will have certain amount of energy, and that energy will come from the initial energy of electron. Hence, instead of this electron moving in a circular orbit like this, because some amount of energy has been removed in the form of radiation, let's say this is the radiations, right? Because of this radiation, the energy of its electron continuously decreases, and hence it cannot follow the circular path, but instead it should follow a spiral path. And ultimately what should happen is, ultimately this electron should collapse onto the nucleus, and thus making atom unstable, right? So this is gradual decrease in the distance between the electrons and the nucleus. So this was the main issue with the Rutherford's model, right? Consequently, the orbit will become smaller. So the orbit will become smaller and smaller, right? And electron would fall in the nucleus. In other words, the atom should collapse. The calculations have shown that it should take only about 10 raised to power minus 8. So time required for this should be around should have been around 10 raised to power minus 8 seconds per electron to spiral into the nucleus. However, this never happens, right? Because we know that at the end of the day, the atom is stable, right? Therefore, Rutherford model cannot explain the stability of an atom if the motion of electron is described on the basis of classical mechanics and electromagnetic theory, right? So obviously, we may think that if the motion of electron in orbit leads to instability of atom, then why not consider the electron as stationary around the nucleus? So instead of this, we can just consider that a natural thought comes to our mind is if this moving theory is not able to explain the behavior, we should just be able to see that we can just assume that the electron is stationary around the nucleus. However, that is also not true. Why? Because if the electrons were stationary, the electrostatic attractive force between the nucleus and the electrons would pull electrons towards the nucleus, right? To form a model described by Thomson model, right? As per Thomson's model, what we had is we had an electron positively charged, uniformly distributed with electrons embedded into it, right? So both of these things could not be true, right? Hence, Rutherford's model also explained that the existence of certain definite lines in a hydrogen spectrum, right? It could not also explain the uh, the certain lines in the hydrogen spectra, right? So one is what we have seen. The other drawback is Rutherford's model could not explain or failed to explain the existence of certain definite lines in the hydrogen spectrum, right? If the electrons were to lose energy continuously, as discussed, right? Just now we discussed the atomic spectrum of hydrogen should have been continuous. However, the spectrum of hydrogen we already know has been found out to be discontinuous in the form of characteristic lines of different definite wavelengths, right? If the electrons were to lose energy continuously, right, the atomic spectrum of hydrogen, the hydrogen spectrum of hydrogen should have been continuous, right? However, we know that that is not true, right? However, the spectrum of hydrogen has been found out to be discontinuous, right? Hence, Rutherford model could not explain this behavior. Hence, a new theory was required, and this theory was given by Niels Bohr, and it is called as the Bohr's model of atom, right? So that is what we are going to study next. Bohr's model of atom. Right, to overcome the drawbacks of Rutherford model of an atom and to explain the line spectrum of hydrogen, Niels Bohr, right? So this was given by Niels Bohr in 1913, proposed a model of atom which was based upon Planck's quantum theory of radiation, right? And the new model is called as Bohr's model of atom, right? So to overcome the drawbacks of Rutherford's model of atom, and to explain the line spectrum or the discontinuous line spectrum of hydrogen, right? Niels Bohr in 1913 proposed a model of atom which was based on Planck's quantum theory of radiation, right? Which is what we are going to study, right? So we are going to study the postulates of Bohr's atom or Bohr's theory or model. Right? The first postulate was an atom consists of a small, heavy, positively charged nucleus in the center, surrounded by electrons, right? And electrons in an atom revolve around the nucleus only in certain selected circular paths, right? So it's not that the all electrons can occupy all the energy levels. There are energy levels, and electrons of only one energy level can translocate or can go to the larger energy level only if there is sufficient energy. So let me write this down. Right? The electrons, the sub postulate of this is that the electrons in an atom revolve around the nucleus only in certain selected circular paths. So this is very important. Cannot have all the energy levels, right? Which have fixed value, radius and energy, right? Fixed value of radius and energy, right? So this is very important. Fixed value of radius and energy, right? And these parts are called as circular paths are called as orbits. And these orbits are associated with the well-defined energies and are called as energy shells or energy levels, right? So these are numbered as 1, 2, 3, 4 and etc., right, from the nucleus, or alternatively K11. So I will show you the figure, but before that, these paths are called as orbits, and these orbits are associated with definite energies and are called as energy shells, energy levels, right? Right, and these are numbered as 1, 2, 3, 4. So in order to understand this, let me drag a picture. Okay. So this is right. So as per what was the problem with Rutherford? With Rutherford, we had that electrons should continuously lose energy and finally collapse onto the nucleus, right? But as per Bohr models, the electrons, they do revolve around the nucleus and they do follow a circular path. However, the energy levels are not continuous. That means an electron, let's say this is an electron, right? So it is moving. Let's say this is an electron. This is right. This is an electron moving in this orbit, right? Like this, in this direction. So it cannot occupy this energy level, right? Or it cannot occupy this energy level. There is no path between these two. There is a gap between these two, right? It can only, from this energy level, it can only jump to this energy level, right? It can only jump to this energy level. There is nothing in between like this, right? So because of this, what we know, what we have is electrons does not continuously lose energy, right? As per the electromagnetic radiation, and which was the problem with the Rutherford's model, right? Let us move on to the next page, right? Then the second postulate, right, was that the energy of an electron in the orbit does not change with time. So this is also very important. So the second postulate, the energy of an electron, right, in the orbit does not change with time, right? This is very important. So from this, what we see is if the electron is at this position, right, is at this position, irrespective of the time, the energy when it is revolving in this orbit is going to remain same. Let's say the energy is C1. So irrespective of whether time is t is equal to 1 or time t is equal to 2 or time t equal to infinity, the energy of this electron is going to remain the same. Hence, we can say that it maintains its orbit in this way, right? That is the main reason, right? So in other words, as long as the electron remains in a particular orbit, it does not lose or gains energies, right? This means that the energy of electron in a particular energy shell remains constant, Therefore, these orbits are also called as stationary states or allowed energy states, right? And the term stationary does not mean that electron is stationary, but it means that the energy of electron does not change with time, right? And this accounts for the stability of an atom, right? Let me write this down. So the sub point of this is the first sub point is, in other words, as long as the electrons remain in a particular orbit, it does not lose or gain energy. So this is very important. It does not, right? What does this mean? This means that the energy of the electron in a particular energy shell remains constant. Okay, so this is important. Hence, what we say is that therefore these orbits are also called as stationary states or allowed energy states, right? And the point which is to be noted here is that the term stationary does not. Let me write this down with does not mean that the electrons are stationary, but it means that the energy of the electron does not change with time, right? This accounts for the stability of atom, right? So the third postulate of this theory is only those orbits are permitted in which the angular momentum of the electron is a whole number multiple of a quantity, right? Only those orbits are permitted in which the angular momentum of the electron is a whole number multiple of a quantity which we call is h by 2 pi, where h is the Planck's constant and pi is the normal pi with a value of 3.14. This is also called as h cross, right? Now why is this? So an electron, like any other moving body, is moving in a circular orbit, has an angular momentum, right? So and what is the formula for angular momentum? It will be nothing but linear momentum multiplied by the distance, that is mv into r, right? Where m is the mass of electron moving with the velocity v and r is the radius of the Bohr orbit, right? Thus, according to Bohr, the angular momentum is a has to be whole number multiple of this h by 2 pi or h cross by 2 pi. So this postulate therefore introduces the concept of quantization of angular momentum, right? So the sub point of this is the electron like any other moving body moving in a circular orbit has an angular momentum equal to, so the it will be mvr, where m is the uh, m equal to mass of electron, p is the velocity of electron, and r is the radius of orbit, right? So as per this postulate, what we have is we should have this mvr has to be some n times, where n is a whole number, multiplied by h by 2 pi, right? Right. So in other words, this postulate introduces the concept of quantization. So quantization means uh, limited. Quantization means conservation, right? Quantization means conservation. Quantization of angular momentum, right? Hmm. And then the fourth observation, the fourth postulate is the energy is emitted or absorbed only when the electron jumps from one energy level to another, right? The energy is emitted or absorbed only when the electrons jump, right? Electron jumps from one energy level to another. So when energy is supplied to an atom, its electron absorbs one or more quanta of energy and jumps to the higher energy level, right? So this higher energy state of an electron is called as its excited state, right? The higher energy state of electron is called as excitation state. Excitation state, right? For example, let me drag a figure. So let us consider this as a figure, right? So for, right, when electron absorbs, so let's say this is the, so for A, whether the figure explains the energy changes in an electron jump, right? So let us say this is the initial position of electron and the energy at this point is E1, right? Let's say this is E1 and this is E2, right? So clearly E2 is greater in energy, right? So magnitude of E2, right? E2 has a higher, E2 is at a higher energy level than E1, right? So whenever this electron has to go from this orbit to this orbit, it has to absorb energy, right? And the absorb energy will be equal to what? This E2, energy of this level minus energy of this level, right? So energy absorbed will be E2 minus E1, right? And this state in this case would be called as a excited state, right? Because this is the original state, right? So this is called as excited state, right? And when the electron once left, now electron has gone from this shell to this shell, and now it is excited. So now electron can come back to this state again to its original position only when it emits a radiation which has an energy equal to E2 minus E1 and it loses this E2 amount of energy, right? So this is an energy E2, this is an energy E1. So it will emit the radiation, right? So this says this is a radiation. So this is basically absorbed radiation. Radiation absorbed, right? And this is radiation emitted, right? So when it goes from there, so energy absorbed, energy emitted will be E2 minus E1, right? Or you can remove the mod signature, right? So here also we have mod E2 greater than mod E1, right? So when electron absorb energy equal to E2 minus E1, it jumps to a higher energy level. And when electron jumps back to lower energy level, it radiates the same amount of energy, right? And this amount of energy emitted or absorbed is given by the difference of energy between these two energy levels, right? E2 minus E1, where E1 and E2 are the energy levels of those particular orbits, right? This means that the emission and absorption of energy occurs only in discrete value, right, which is equal to the difference in two energy levels, right. So in other words, the energy of electron cannot change gradually and continuously, but changes abruptly as the electron jumps from one energy level to another, and not in any value, right. And this explains the fact that atomic spectra are discontinuous, right. So let us write this down, right. This means that the emission or absorption of energy, right, occur only in discrete value, right. So in other words, what we can say is, so in other words, the energy of electron cannot abruptly, right, abruptly, but as the cannot change, sorry, cannot change gradually, right. Sorry, cannot change electron cannot change gradually and continuously, right, but changes abruptly, right, as the electron jumps from one energy level to other, and not in any value, right? Right? And this explains the atomic spectra. This explains the fact that atomic spectra are discontinuous, right? Right. And now let us discuss about the successes of Bohr's model. So based on these uh, postulates, the model which was proposed by Bohr, and how it could explain some of the unexplained things, right? Right. So success of Bohr's model, right? Success of Bohr's model. The first success which we see is Bohr's atomic model explained the stability of atom, right? Bohr's atomic model explained the stability of atom. So according to Bohr model, an electron revolving in a particular orbit cannot lose energy, right? And therefore, the emission of irradiation is not possible as long as the electrons remain in one of its energy level, and hence there is no cause of instability in his model, right? The second one is Bohr's concept of atom explained successfully the atomic spectrum of hydrogen atom, right? Bohr's concept of atom explained successfully the atomic spectrum of hydrogen atom, right? So from the Bohr's model or atomic model, it is clear that the electrons can have only certain definite energy levels, right? When electron is present as close to nucleus as possible, the atom has the minimum possible energy and is said to be in ground state, right? For example, in the case of hydrogen atom, there is only one electron, and this should mean that electron is present at the lowest energy level, that is closest to the nucleus, that is with n is equal to 1, and this represents the ground state for hydrogen atom, right? When energy from one when energy from some outside source is supplied to it, it can absorb a definite amount of energy and jump to higher energy state, right? Such a state of an atom in which the atom possesses more energy than possessed in the ground state is, we already know, is called as an excited state, right? Thus, for hydrogen atom, first energy level, which is n equal to 1, is called ground state, and higher energy level with n value greater than 2 are called as excited state, right? This excited state is unstable, right? And the electron tends to come back to a lower energy level. And this transition, right, that is change from upper to lower energy level, occurs with a jump, and energy is emitted in the form of quantum equal to difference in energies between the two levels, right? In order to understand this, let us drag an image, right? So let's say, right, this is the ground state energy, right, and this is the excited state energy, right? So the quantum of radiation which is coming out, the energy, only we know that energy is only absorbed or emitted in the form of uh, discrete values, right? So when this quantum of energy, right, so this excited state is unstable, and the electron tends to come back to its original position, right, like lower energy value. And this transition, that is change from upper to lower energy level, occurs with a jump, and energy is emitted in the form of radiation, right? So this is the form of radiation, right? Right? In the form of radiation. For example, if electron comes back from this energy state to this energy state, the energy level difference will be E2 minus E1, which is nothing but the energy of the associated wave, which is h into nu, right? The energy would be given by h into nu. Therefore, the frequency of the emitted radiation would be given by how? Right? So this is nothing but energy, right? Yes, which is nothing but E2 minus E1, which implies mu is nothing but E2 minus E1 divided by h, right? And since E1 and E2 can have only definite values for an atom, hence we will also have fixed value, right? Because this E1 and E2 are fixed. We know that these energy levels like this are not possible, right? Only this energy level and this energy level is possible, right? Hence the amount of energy released will also be some discrete value, and hence the frequency will also be a discrete value, right? Moreover, the energies of different energy level are characteristics of atom, right? So for example, so let's say this is a hydrogen atom. So for E1 and E2 for hydrogen atom will be different than E1 and E2 of helium atom or any other atom, right? So this is to be mentioned in here that E1 and E2 are characteristics of atom under consideration. Right? Hence we see different atomic spectra for different materials, right? Therefore, the emitted frequency will also be the characteristics of atom, right? Right. So let us do some mathematics, right? Hmm. So now we know that this mu will be nothing but E2 minus E1, E2 minus E1 by h, right? Right? Where mu is nothing but c by lambda, right? As mu into lambda is nothing but c, and c is the velocity of light in vacuum, right? Thus, c by lambda is nothing but E2 minus E1 by h, or lambda is nothing but hc by E2 minus E1. Since h and c, right? This h and c are constant, and E2 minus E1 corresponds to definite energy. Thus, each transition from one level to another will produce a light of definite wavelength, right? Let us write down. And this is observed as a line in the spectrum of hydrogen atom, right? Since h and c in above equation are constant, right? And E2 minus E1 corresponds to definite energy, right? Right. Thus, each transition from one level to the other will produce a light of definite wavelength, right? And this is observed as a line in the spectrum of hydrogen atom, right? Right? Now, if the electron jumps from, let's say, now, let's say, for example, here is the figure. Now, if electron jumps down from third energy level to first energy level, right? Having an energy, so this energy of this level is E3, energy of this level is E1, and then the wavelength of this line, right? The wavelength of the emitted radiation would be what? It would be lambda will be what? E3 minus E1 divided by H, right? Let's say lambda dash. This is lambda dash, right? Similarly, if the energy would have been E3, E5 to E3, E5 to E1, then energy would have been, let's say lambda double dash would have been E5 minus E1 divided by H, right? Thus, the different spectral lines in the spectrum of atom corresponds to different transition of electrons from higher energy levels to lower energy levels, right? Thus, different spectral lines in the spectrum of atom corresponds to different transition of electrons from higher energy levels to lower energy levels, right? Right? Simultaneously, now this we talked only for a case of one electron. Imagine if there would have been many electrons, right? So in that case, there would be many spectral lines, right? Simultaneously, appearance of large number of lines in the spectrum of hydrogen could be explained by, let's say this is a heading, simultaneous appearance of a large number of lines in the spectrum of hydrogen, right? Right? So this behavior is quite curious, right? And this is what this you can understand by a presence of many electrons, right? So this so we conclude our lecture here. So in this class, what we have seen is, so in this class we have seen about drawbacks of Rutherford's model, right? Then we studied about Bohr's model, postulates of Bohr model, right? Postulates of Bohr's model, right? Further we studied advantages or how it could overcome the drawbacks of Rutherford's model, right? right? How it could explain the explanation for stability of atom and explanation of emission spectra of hydrogen atom, right? Right? So I thank you all for attending this class, and I hope to see you again in the next class. So what we are going to study in the next class is we are going to study about the explanation for the different series, different lines, right? So we had in the previous class studied about Lyman line, Barman line, right? So we are going to study the explanation for those type of lines from Bohr's model, and then further we are going to study about the further we are going to solve some solved examples, right? And then we are also going to study about Bohr's radius and what would be the amount of energy of each orbital. So how what is the expression for that? That is what we are going to study in the next class, which will be followed by a couple of questions, right? So again, I thank you all for attending this class, and I hope to see you again in the next class, right? Thank you. Hi everyone, my name is Bharat Dow, and I welcome you all to this ninth lecture of structure of atom, right? So my name is Bharat Dow, and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. Right? So in the last class, what we have seen? In the last class, we have seen that the drawbacks associated with the Rutherford's model, right? We saw that the Rutherford's model could not explain the stability of electrons revolving around the nucleus, and also it could not explain the some of the other facts, right? So for this, a new method, a new model was needed, and this model was given by Bohr's model, right? Then we studied about the numerous postulates of Bohr model, right? And then on the top of that, we studied in detail about those postulates, and then at subsequently we studied the advantages of Bohr's model, right? Like what factors which with the Rutherford's model was not able to explain, that were we could successfully explain with the help of Bohr's model. So we studied about that, right? Then we explain we explain the stability of atom, that is the advantage of Bohr's model above Rutherford's model, and we explain the emission spectra of hydrogen atom, right? So in this class, what we are going to study, we are going to study about numerous other aspects of Bohr's model. Like we are going to study the reason behind simultaneous appearance of large number of spectral lines, right, in the spectrum of hydrogen. Further, we are going to study about the Bohr radius or the significance of other energy levels, and we are also going to study about explanation for line spectrum of line hydrogen, and then further at the end we are going to solve some examples, right? So let us start. Right. The first topic, let me write the heading: structure of atom. Right. Lecture 9. The first topic which we are going to study is the explanation for simultaneous appearance of a large number of lines in spectrum of hydrogen. So if you remember, in the previous classes, we have studied about various series like Lyman series, Balmer series, right? So we are going to study the explanation for this, right? So this behavior is quite curious, and a question arises as to why hydrogen atom gives so many spectral lines, right? Although it contains only one electron, right? So even though hydrogen has only one electron, there are many lines in emission spectra of hydrogen, right? So this was the question: why, right? So in fact, any simple gas of hydrogen, any sample of gas, So in fact, any sample of hydrogen gas contains a large number of atoms, and when energy is supplied by passing electric discharge, the electrons in the different hydrogen atom absorb different amount of energies, right? Therefore, these are raised to different energy level state, right? For example, the electrons in some atoms may jump to secondary energy level, right? While in some, in others, they may be raised to third or fourth or any n energy levels, right? Now the excited electrons come back from these higher energy levels, right? So let me first, in order to understand it, let me first grab a figure. So if you look at this figure, so let us just try to understand it from the example. So let us consider some electrons are present in fourth energy level, right? Some of these electrons will directly jump from fourth energy level to the ground state, right? Via route A, right? Whereas others may jump from, let's say for example, if they are coming from fourth energy level to two energy level, and then second energy level, first excited state to the ground energy level, or some of them might come from fourth energy level to third energy level, and then from third to direct ground energy level, or vice versa, right? From fourth to third, third to second, and second to first, right? So some of these electrons may directly jump from ground state, right? Ground state, directly jump to the ground state. Others may jump to second energy level state and then to first energy level state, while others may just drop third, fourth, right? Like this, right? So these are the four routes, right? For this example, we have these four routes, right? So when these excited electrons jump back to various energy level states, they emit different amount of energy, right? And this results into different hydrogen lines depending upon the differences in energy level, right? So let us write this down. So this is one. So we are going to write any sample of hydrogen. Any sample of hydrogen gas contains large number of atoms. When energy is supplied, right? When energy is supplied by passing electric discharge, right? So any sample of hydrogen can contains a large number of atoms, and when energy is supplied by passing electric discharge, the electrons in different hydrogen atoms absorb different amount of radiation, right? Therefore, these are raised different energy states. For example, figure on next page, right? So this figure, what is what we are talking about, right? Right. So when, for example, when electrons jumps from all energy levels other than n equal to 1, right? Right. If electrons are jumping directly from any energy level to this n equal to 1 directly, then the lines which we obtain are called as are in all fall in ultraviolet region, and these lines are called as Lyman series, right? Similarly, the lines obtained when electron jumps to second energy level, right, directly to the second energy level, these fall under visible region, and these are called as Balmer lines. So if I were to tell you using image, so you can see this is the image, right? So if from any energy state the electrons directly go to the ground energy state, then we call it as a Lyman series, right? And these all lie in ultraviolet region. So let's say this is initial state and it directly goes to ground state, or it is at this stage and it directly goes to this. Then in such cases we call this a Lyman series, right? And when it goes to n equal to 2, right, then we see it's a Balmer series. Similarly, when it falls from any energy state to directly n equal to 3, we call it as Paschen series. Similarly, when n is equal to 4, it's bracket, and when n is equal to 5, it's found, right? So one thing which you can notice in here is that the energy gaps, right? This is the energy gap, let's say delta E1. This is the energy gap. This is, let's say, delta E2. This is delta E3. Similarly, as we go above, as we go from lower energy to higher energy, the energy gap is decreasing, right? And this is not just for the pictorial representation. It is actually a fact that as we go from energy, lower energy to higher energy, the gaps in the energy level decreases, and that we are going to study further one, right? So the origin, right? So this is by this we have seen. Similarly, the lines obtained when electron jumps to second energy level and equal to 2 from higher energy level is called as Balmer series, right? This is a Balmer series, right? In a similar manner, the transition from higher energy level to n equal to 3 produces Paschen series, right? Similar is the case with bracket and bound series, right? So let us try to do it. So there exists a relationship. So that is what we are going to study. Okay, it's a note. In general, the number of emission lines when an electron jumps from N2 level to N1 level are given by the relation. So this is the expression for that number of lines equal to N2 minus N1 into N2 minus N1 plus 1 divided by 2, right? This is a very important expression, right? Right. So for, let's say, for example, in the Lyman series, when an electron drops from fifth level, that is what N2 is equals to 5 to ground state. Is what N1 equal to 1. Then what we have is number of spectral lines. Would in that is be what is 5 minus 1 multiplied by 5 minus 1 plus 1 divided by 2, which corresponds to 20 by 2 by 10, right? And how would these lines be? These lines would be in this following manner, right? So it will, let's say it's at 4. So it will go from 4 to 5 to 4, then 4 to 3, 3 to 2, and 2 to 1, right? So these are around 4 lines. Let's say it's at 4, 4 to 3 it will go, right? Then it can go 4 to 2 or 4 to 1. So these are 3 additional lines, right? And then 3 to 2 it can go, or 3 to 1 it can go. So these are 2 lines. Then 2 to 1 it will go, right? This is 1 line. The total lines 4 plus 3 plus 2 plus 1, which is 4 plus 6, which is 10, right? So let us move on to the last postulate, right, of Bohr's model. No, the advantage of Bohr's model, right? Number 3, right? Bohr's theory helped in calculating the energy of electron in a particular orbit of hydrogen atom, right? So Bohr's theory helped in calculating the energy of the electron particular orbit of hydrogen atom, right? On the basis of postulate, right, Bohr derived a mathematical expression for the energy of an electron moving in a particular orbit of hydrogen atom, right? And in this case, he pictured hydrogen atom as a system consisting of a single electron of mass m and a negative charge E evolving in circular orbit, right? So the expression corresponds to En is equals to minus RH 1 by n square, where n equal to 1, 2, 3, right? Where En is what? En is energy of electron, right? This is the energy of electron in nth orbit. Energy of electron in nth orbit. RH is nothing but our constant. Right? N is the energy level. Alright? And this constant, this RH comes out to be 2 pi square me to the power 4 divided by h square. Right? Hence, when we couple this together, what we get is En is what? Minus 2 pi square m e to the power 4 by h square into 1 by h square. So remember, these all things are positive, right? These things is all positive, right? It means energy has to be negative, right? It's a negative value, right? We are going to discuss about it. Okay. So substituting the known values, we know what is the value of pi, right? 3.14. We know the mass of electron. We know the charge of electron. We know the Planck's constant, right? So when we substitute the values, what we get is En comes out to be minus 2.18 into 10 raised to power minus 18 by n square joule per atom. Right? When we convert it into electron volts, it comes out to be 13.595 by n square electron volt per atom. Why? Because 1 electron volt is what? 1.6022 10 raised to power minus 19 joules. Right? And hence when we rearrange it, it comes up to be minus 1138 by n square kilojoule per mole, or we can approximate it as En is equals to minus 1312 n square kilojoule per mole, right? Thus, for each value of n, there exists a possible energy level for the electron, right? So substituting for n is equal to 1, 2, 3, 4, we obtained the E1, E2, E3, and so on and so forth. So these integral numbers n is equal to n1, n2, n3, n4, expressing stationary state of atom, are known as principal quantum numbers, right? So this is a new terminology, right? Just we are giving the name, right? So these integral numbers n equal to 1, 2, 3, so on and so forth, are called as principal quantum number, right? Right, and let us draw the diagram, right? When we put in these values E1, E2, E3, right? When we put n equal to 1, n equal to 2, and n equal to 3, we get E1, E2, E3, right? So let me just plot it. Right, so let's say here we have an orbit, let's say n value, and here we have energy, kilojoule per mole, right? So let's say this is n equal to 1, n equal to 3, n equal to 3, n equal to 4, and the expression is minus 13118.8 divided by n square kilojoule per mole, right? So when we put in this n values into this expression, what we get is minus 1311.8, right? Minus 327.9, minus 145.7, minus 8, right? So this is what E1, this is E2, this is E3, and this is finally E4, right? So note which has to be discussed in the previous class, right? If you calculate this value, right, it is clear from above, from the above table, that as the value of n increases, right, the energy difference between successive energy level decreases, right? That means E2 minus E1, right, is greater than E3 minus E2, which is greater than E4 minus E3, and so on, right? Right. So now let us move on to the next topic, right? Energy expected, energy expression for, right, energy expression for hydrogen like ions. So for the energy expression for hydrogen like ions, it comes out to be En is equals to minus 2 pi square me to the power 4 n square h square, and here instead of for to account hydrogen like ions, we just put in the z square value, right, which comes out to be minus 2.18 10 raised to the power minus 18 into z square by n square joule, which comes out to be minus 1311.8 into z by n whole square kilojoule per mole, right? Where z is the atomic number, right? Right. So now we'll study about the significance of negative, right? We said that energy is negative, right? Significance of negative electronic energy. Right. So it is clear from the above relation, right? This relation that En is equals to minus 1388 divided by z by n whole square kilojoule per mole. So from this expression, it is clear that the energy of an electron is negative in the hydrogen atom, right? So energy is negative because this is positive as it's a square. So there, so these all terms come out to be positive. This is multiplied by minus 1, right? So what does this negative energy convey, right? The negative sign of energy means that the energy of electron in the atom is lower than the energy of free electron at rest, right? So what does this mean? So what does negative sign convey? Right? So the negative sign, the negative sign of energy means that the energy of the electron is lower than, sorry, the energy of electron in atom is lower than the energy of free electron at rest, right? Energy of free electron at rest, right? So free electron, right? A free electron at rest is an electron that is at sufficiently far away from the nucleus and its energy is assumed to be zero, right? So free electron at rest is an electron that is at sufficiently far away from the nucleus, and its energy is assumed to be 0, right? Okay, so this is important. So mathematically it corresponds to the setting. Mathematically it corresponds to setting n equal to infinity in this equation, right? If you put n equal to infinity in this expression, what we get is the energy of free state electron. So as the electron moves closer to the nucleus due to the electrostatic attraction, work is done by the electron itself, and hence energy is released, right? Consequently, its energy decreases as it takes energy values less than 0, which means negative values, right? So negative sign also indicates that the electron is bound to the nucleus, and a hydrogen atom is in a stable state, is in a stable state in comparison to a state where electron is sufficiently far away from the nucleus, right? So let me write this down. Mathematically, it corresponds to setting n equal to infinity in above equation, right? So as electron moves, closer to the nucleus, right? Closer to the nucleus due to the electrostatic attraction, right? Work is done by the electron itself, and hence energy is released, right? Consequently, right? Consequently, its energy decreases and it takes energy values less than 0, right? Which means negative values, right? The negative sign also indicates that the electron is bound to the nucleus, and hydrogen atom is in a stable state, right? In comparison to a state where electron is sufficiently far away, sufficiently far away from the nucleus, right? The next topic which we are going to study is the Bohr radius, right? Radius of atom, right? It's called Bohr radius. So Bohr also calculated the radius of first or the ground state of hydrogen atom, and the rest this corresponds to n square h square divided by, so the ground state radius comes out to be around, is represented by r0 and comes out to be around 52.9 nanometers, picometers, sorry, right? Right? And the expression for nth orbit's radius comes out to be n square h square divided by 4 pi square me square z, right? For hydrogen, z is equals to 1, right? So hence Rn is equals to, let us combine this A0 into n square, right? Rn is equals to A0 n square, where A0 is nothing but R0, which is 52.9 picometer, right? Right? So R0 equal to A0 equal to 52.9 picometer is the radius of first stationary state called the Bohr radius, right? Which is 52.9 picometer, and in terms of Armstrong, it corresponds to 0.529 Armstrong. Right? So Armstrong is nothing but 10 raised to the power minus 10 meter, right? Similarly, for n equal to 2, Rn is R2 and R2 is 0.529 into 2 square, which corresponds to, right, or 52.9, which corresponds to 2116 picometer, right? So on and so forth, right? For hydrogen like atoms, for hydrogen like ions, the expression comes out to be A0 n square by z, right? Instead of z square, it comes out to be z, right? Right? Or in other words, if you want to use the value of A0, it comes out to be Rn is equals to 0.0529 n square by z, right? Nanometer, right? Then it's very important expressions which we are going, okay? The next would be velocity. Velocity of electron in any orbit, right? So velocity expression for that comes out to be velocity is equals to nh by 2 pi mr, right? Where r is nothing but, let's say, Rn Vn. So Rn is nothing but A0 n square by z, right? Then in that case, Vn comes out to be 2 pi e square z by n into h, right? So this is important. And then if we substitute all the known values, so we know value of pi, value of e, right? And sorry, and not h we know. And so if we substitute these known values, it comes out to be Vn is nothing but 2.19 into 10 raised to power 6 z divided by n in meter per second. And if we say the velocity, let's say V0 is the velocity of electron at ground state, then V0 comes out to be how much? V0 comes out to be 2.19 10 raised to power 6 meter per second, and the expression changes to Vn is equals to V0 into Z by N, right? So this is very important expression, right? Then further, if you want to calculate number of revolutions made by an electron around nucleus, so number of revolutions comes out to be V by 2 pi r, and when we substitute the value of r, right, which we calculated, it comes out to be number of revolutions are nothing but 2 pi mv Z square by n square h square, right? So these are all very important expressions which one should remember, right? This is very important, right? Right? So now let us try to solve some problems, right? So the question one, if the energy difference between the electronic states of hydrogen atom is 214.68 kilojoule per mole, what will be the frequency of light? What will be the frequency of light emitted when the electron drops from the higher to the lower energy state? Right? We know that also Planck's constant has been given to us as 39.79 10 raised to power minus 14 kilojoule second by mole. Right? This has been given to us. So this is a very simple problem. So we know that frequency, that is nothing but mu of emitted light, is related to the energy difference of two energy levels, which is nothing but delta E, as delta E is nothing but h nu, which is nothing but hc by lambda. Right? We are already given delta E value, which is 214.68 kilojoule second per mole, and we are also given h value, which is 39.79 into 10 raised to power minus 14 kilojoule second by mole. Right? Hence mu is nothing but delta E by h, which is 214.68 divided by 39.79 10 raised to power minus 14, which is nothing but 5.39 into 10 raised to power 14 second inverse, right? Hence mu is nothing but 5.39 10 raised to power 14 second inverse, or 5.39 into 5.39 into 10 raised to power 14 hertz, right? So this is the answer. Right? Let us move on to the next question. So question number 2. This is important. So according to Bohr's theory, the electronic energy of hydrogen atom in the nth Bohr orbit, right, is given by following expression. En is nothing but minus of 21.76 into 10 raised to power minus 19. Let me rephrase it. Minus 21.76 into 10 raised to power minus 19 by n square joule per atom. Right? Now what we have to do? We have to calculate the longest wavelength of light that will be needed to remove an electron from the third orbit of He plus atom. He plus ion, right? Right. So here for hydrogen like ions, right, that is He plus ion, we know En is given by 21.76 10 raised to power minus 19 z square by n square joule per atom, right, where z is nothing but atomic number, right? For He plus z is 2, right? And as we know that it's a third orbit, we know this. We just put it the expression values 10 raised to power minus 19. So here z is what? 2 by n square. What is n? N is 3, right? Joule per atom, right? Now the energy required to remove an electron from third Bohr orbit of He plus ion is going to be what? Delta E, right? Which is nothing but E3 E alpha minus E3, right? At infinite. So this will be the energy infinite, which is nothing but 0 minus of minus this value, right? 21.76 10 raised to power minus 19 2 by 3 whole square, right? And this energy is certainly going to be hc by lambda, right? This energy is going out to be h nu, which is nothing but hc by lambda, right? Hence we can say h nu, which is nothing but delta I, which is 9.67 into 10 raised to power minus 19 joule, right? Hence this is hc by lambda. Hence lambda is what? Hc by 9.67 10 raised to power minus 19, right? So when we put in the values, we get 6.626 10 raised to power minus 34. That is the value of H multiplied by 3 into 10 raised to power 8. That is the volume, or that is the value of C. That is the speed of light divided by 9.67 10 raised to power minus 19. right? And hence lambda corresponds to be around 2.055 into 10 raised to power minus 7 meter, or lambda is equals to 205.5 nanometer, right? So this is the answer, right? So in summary, what we have studied today, we have studied the last advantage of Bohr's model, right? Why multiple lines are present in emission spectra of hydrogen atom, right? Further, we have also studied about the Bohr's expression for, or Bohr's radius for nth orbit, also velocity or velocity expression, right? Velocity expression for electron in nth orbit. Further, we have also solved some problems. So this is where we conclude today's class. So in the next class, what we are going to study about, we are going to study about the dual nature of matter. That means we are going to study about de Broglie wavelength, and then we are also going to study about its origin. Then we are going to study about wave nature of electrons, that is the different experiments like diffraction and inference, the Davis and German's experiment. And then we further study the Bohr's postulate of quantization of angular momentum from de Broglie's wavelength, right? And then in the end, we'll also study about the Heisenberg uncertainty principle, right? So I thank you all for attending this class, and I hope to see you all again in the next class. Thank you. Hello everyone. I welcome you all to this 10th lecture of structure of atom. I am Varat Dao, a doctoral student and also a Prime Minister Research Fellow at the Department of Chemical Engineering at IIT Kanpur. So in the last class, we have studied about the advantages of Bohr's model, right? And certain explanations which could only be explained by Bohr's models and could not have been explained by other previous models, like for example Rutherford's or some Thomson's model. So we were using these concepts of Bohr's model. We established that we were able to successfully explain why multiple lines are present in the emission spectra of hydrogen atom, right? Further, we also found out what is the Bohr's radius for the nth orbit and the velocity expression for electron in the nth orbit. Further, we also solved some 4 to 5 examples which could explain the how to apply this expressions which we derived in here, right? In today's class, what we are going to study is we are going to study the concept of quantization of energy given by Bohr, right? And then further, we are also going to study the limitations of Bohr's model and how these limitations arise. Like for example, we are going to study about the uncertainty principle given by Heisenberg, and dual particle nature, dual wave and particle nature of matter, right? So that is what we are going to study. So let us begin. Structure of atom. First topic is Bohr's theory and concept of quantization. So noticeable achievement of Bohr's theory of structure of atom was that it could predict the values of energies which an electron can have while revolving around the nucleus of hydrogen atom, right? So just say A. Bohr's theory could predict the energy of electron in the nth orbit, right? According to Bohr, the electron in the hydrogen atom can have energy values given by the relationship, right? So energy of an electron in the nth orbit, this has to be in subscript is equal to minus 13118 divided by n square kilojoule per mole, where n is equal to 1234, right? It should be a whole number. So in other words, n cannot have a fractional value, so that the electrons cannot have all possible values of energy, but only those values for which n is a whole number, right? So we also concluded this, right? That energy is discretized. Energy is discretized and not continuous, right? For electron, right? Thus, electron can only take certain fixed values of energy. It means that when an electron gains or loses energy, it does so in such a way that n has a value which is a whole number, right? So in other words, electron does not gain or lose energy in a continuous manner, but in jumps, right? So this led to the concept of quantization of energy, which means that the radiant energy is emitted or absorbed in burst rather than continuously, right? From above facts, we can conclude that the energy of an electron is quantized. In other words, electron does not gain or lose energy in a continuous manner in jumps, right? What does this mean? This means this led to the concept of quantization of energy, right? So let me write this. Quantization of energy, right? This means that radiant energy is emitted or absorbed in bursts or jumps rather than as continuous burst. This is very important. From above, it can be concluded the energy of electron is quantized, right? The quantization concept may seem to be mysterious, right? But it is very easy to understand, right? So if you take this as a grid, the discrete energy levels in Bohr's model may be compared with the steps of a ladder, right? Right. So let us consider this is the first step of ladder, second, third, fourth, or you could also say that these are the energy levels. Actually, as we go up the energy level, the gaps in the energy decreases. However, which is not shown in here. However, you can consider it, right? So imagine a ladder having the steps labeled as this 1, 2, 3, 4, and 5. So your position on the ladder can only be a step and never in between, right? So these steps in the ladder are similar to the energy levels or orbits in atom, right? The we can do like this. The discrete energy levels, the discrete energy levels, right, in Bohr's model may be compared with steps of ladder. And imagine a ladder having steps labeled as 1, 2, 3, so on and so forth, right? So your position on the ladder can only be a step and never in between, right? That means you can be in a ladder 1 or ladder 2 or step 1, step 2, step 3, but you cannot be at a step 1.5 or 2.5 or 3.6, right? That is what we mean by this, right? So these steps in the ladder can only be step sorry so these steps in the ladder are similar to energy levels or orbits in an atom, right? So let us move on to the next topic, that is the limitations of Bohr's atomic theory. So even though Bohr's atomic theory was able to predict and explain many behaviors, it still failed to explain some experimental observations, right? The limitations of Bohr's atomic theory. Right? So Bohr's theory of atomic structure was quite successful in explaining the stability of atom and the line spectra of hydrogen atom. However, several discrepancies were observed in this model. Some of the limitations of Bohr's model, right? So the first limitation of Bohr's model was Bohr's model of an atom could not account for the finer details, right? For example, duplet, that is the two closely spaced lines of the hydrogen spectrum observed using sophisticated spectroscopic techniques, right? So it could not explain the very close two lines which are very close in atomic spectra of hydrogen, which were experimentally were obtained using the complicated or sophisticated experimental measures, right? Or spectrometers, right? So Bohr's model of an atom. Bohr's model of an atom could not account for the finer details. Like for example, duplet. Let me use a different color for this. Duplet, which are two closely spaced lines of hydrogen spectrum observed using the sophisticated or very accurate spectroscopic method techniques, right? So Bohr's model of an atom could not explain the, so the second point is the Bohr's model of atom could not explain the line spectra of atoms containing more than one electron, right? According to Bohr's theory, on one and only one spectral line can originate from an electron between two energy levels. But if a powerful spectroscope is used, certain single lines are found to split into a number of very closely related lines, right? The existence of such line could not be explained on the basis of Bohr's theory. Right? So the second drawback of Bohr's theory was that Bohr's model of an atom could not explain the line spectra of line spectra of atom, line spectra of atoms containing more than one electron, right? According to Bohr's theory, one and only one spectral line, one and only one spectral line can originate from an electron, right? Can originate from electron, right? So originate from an electron, right? Between any two energy levels. between any two given energy levels, right? But if a powerful spectroscope is used, certain signal lines are found to split into a number of very closely related lines, right? And the existence of such lines could not be explained based on Bohr's theory, right? The existence of such lines could not be explained on the basis of Bohr's theory. The third drawback of this Bohr's model was that the Bohr's theory failed to account for the effect of magnetic field on the spectra of atoms or ions. It was observed that when an atom emitting radiation is placed in a strong magnetic field, each spectral line is further split into a number of lines, and this phenomenon is known as Zeeman effect, right? So it could not explain this Zeeman effect. So Bohr's theory failed to account for the effect of magnetic field on the spectra of atoms or ions, right? It was observed that when the atom emitting radiation is placed in a strong magnetic field, each spectral line is further split into a number of lines. Right? And this phenomenon is known as Zeeman effect. So it could not explain the Zeeman effect. The fourth drawback was Bohr's theory also could not explain the effect of electric field. Right, similar to magnetic field, it could not also explain the effect of magnetic field on the spectra of hydrogen atom. Right, and this effect is called as Stark effect. Right, Bohr's theory also could not explain the effect of electric field known as Stark effect on the spectra of atoms. Right. The fifth one is that Bohr's theory does not provide any clue to explain the shapes of molecules arising out of directional bonding between the atoms. Right. So Bohr's theory does not provide any clue to explain the shapes of molecules arising out of the directional bonding between the atoms. Right. This was also one of the major drawback. Bohr's theory does not provide any clue to explain the shapes of molecules arising out of the directional bonding between atoms. Right? The sixth and the major drawback of this model was the main objection to Bohr's theory came from the new principle, namely the dual nature of matter and uncertainty principle. Right? So they introduced the idea that a wave character of electron, in addition to its particle character, and pointed out that the path of the motion of electron cannot be well defined. Thus, this overruled the Bohr's idea of well defined circular orbits. Right? So this dual nature of matter said or predicted that we cannot define the path of electron precisely. However, Bohr's atom precisely told that the path of electron will be a circular orbitals, right? So this was the major blow to Bohr's model. Thus, we find that Bohr's model was only partially successful. It explained some experimental results, but was unable to account for many other features of the atom. Therefore, it was abandoned in the light of modern ideas regarding the wave characteristics of matter. Right. The main objection to Bohr's model. Bohr's model or Bohr's theory came from the new principles, namely the dual nature, which we are going to study, right? And uncertainty principle. Right? They introduced the idea the idea of wave character of electron, right? In addition to its particle nature. In addition to its particle character. And pointed out that the path of electron path of motion of electron cannot be well defined. Right? Thus, this overrule the Bohr's idea of well defined circular paths. Right? And hence the Bohr's, because of these many limitations of Bohr's model or disadvantages of Bohr's model, this Bohr's model was abandoned and a new model was proposed. Right? So now what we are going to study is we are going to study the dual nature of matter, right? And the experiments which proved it, right? Model. What we are going to study is modern concept of structure of atom. Which is quantum mechanical model. To overcome the shortcomings of Bohr's model, attempts were made to develop a new, suitable, and general model of an atom. So, two important developments which contributed significantly in the formulation of new models were: number one, the dual nature of matter, and the Heisenberg's uncertainty principle. Right. So, let us first study the dual nature of matter. Dual nature of matter. So Einstein had suggested that light can behave as a wave, as not only as a wave but also like a particle, right? In his dual character. In 1924, de Broglie suggested that just as light exhibits wave and particle properties, all microscopic materials, all microscopic material particles such as electron, protons, atoms, and molecules, they also have dual character, right? So they behave as a particle as well as a wave. This means that an electron, which has been regarded as a particle, also behaves like a wave. Thus, according to de Broglie, all material particles in motion possess wave-like characteristics, right? So let me write this down, right? So what de Broglie suggested in 1924, in 1924, de Broglie suggested that just like light exhibits wave and particle properties, right? Wave and particle properties. So does all other microscopic material, right? Microscopic material particles, right? Or microscopic material particles such as electron, protons, atoms, etc. have also dual character, right? They behave as a particle as well as a wave, right? They behave as a particle and as a wave, right? This means that an electron which has been suggested regarded as a particle also behaves like a wave, right? Then according to de Broglie, all material particles in motion, right? This motion word is very important. All material particles in motion possesses wave characteristic, right? So according to de Broglie, the wavelength associated with the particle of mass m moving with velocity v is given by, right? So I will write, so according to de Broglie, the wavelength associated with a particle of mass m moving with velocity v, right, is given by the relation lambda is nothing but h by mv, which is lambda by p, right? Or h by p, sorry, because mv is nothing but momentum, right? So p here stands for momentum, right? Where let us write h equal to Planck's constant, p is equals to velocity, E is nothing but mass into velocity, which is momentum. Right? And these waves are called as de Broglie waves. Right? So now you see that from this expression that the wavelength is also is inversely proportional to the mass. Right? That means more the mass, lesser the lesser the wavelength, and lesser the mass, more is the wavelength. Hence, for a macroscopic objects like uh, anything beyond electron or proton, the mass is so high that the wavelength becomes less, and hence the particle nature of matter becomes dominant over the wavelength nature. Whereas for mass of subatomic particle level, that is proton and electron, the mass is sufficiently low that the particle nature is not dominant. However, wave nature becomes dominant over particle nature of light. Right. So now let us derive the de Broglie's wavelength formula. Right. So this expression let us derive derivation of de Broglie relationship. Okay. The relationship may be derived by combining the mass energy relationship proposed by Max Planck and Einstein. Right. So the relationship may be derived by combining the mass energy relationship proposed by Max Planck and Einstein. Right. So according to Planck, photon of light having an energy, right? Photon of light having energy E is associated with a wave of frequency mu, right? And this energy would be given E is equals to h nu, whereas according to Einstein, the energy would be E is equals to m into c square. But the energies are same, right? That means equation 1 and 2 equating equations 1 and 2 we get h nu, h into nu is equals to mc square, right? But we know v into lambda is nothing but c, right? This is frequency, right? That means frequency is nothing but c by lambda. Hence we put this hc by lambda is nothing but mc square, right? That means h by lambda is m into c, right? Which implies lambda is nothing but h by mc, right? This expression is valid for photon, right? Moving with velocity c. This expression is valid for a photon moving with velocity, which is nothing but speed of light, right? But if we exchange this with a particle of mass m and its velocity v in place of velocity of light, then the equation would become this one. So, de Broglie suggested that on substituting the mass of the particle m and its velocity as v in place of velocity of light, the equation can also be applied to material particles, right? and the expression then will become lambda is equals to h by m into b, right? This expression is known as de Broglie's equation, right? Now, let us move on to the next topic, which is justification for dual nature of electron. So this was given by the Davis and German's experiment of interference and diffraction, right? So let me grab an image, right? So before that, the particle and wave nature of electron can be justified on the basis of following observation, right? A particle nature, right? So dual nature means we should have a particle nature, an experiment which correctly justifies that the electron is nothing but a particle, and then at the same time another experiment which justifies that it's a wave nature, right? So that is what we are going to study, right? So particle nature electrons. So let me first drag a figure. So in this figure depicts the electron diffraction experiment performed by Davis and Germer, right? So electrons exhibit the characteristics of particle. They have a definite mass, right? When the electron strikes a zinc, so this is for the wave nature of light, right? So wave nature. So the wave nature of electrons was experimentally verified by Davis and Germer in 1927 and George Thomson, right? So this is called as Davis and German experiment. Let me write it down. Davison and Germer's experiment showing interference and diffraction. So Davis and Germer subjected the streams of, right? So this is a monochromatic, the subjected streams of electrons, right, from a tungsten filament. So this is a tungsten filament, and beam of electron was ejected from here, right? The influence of strong electric field so as to accelerate the speed of electron. When these electrons were made to strike against the nickel catalyst, the concentric dark and bright fringes were observed, right? So these are the dark and bright fringes which were observed, right? So these rings were called as diffraction ring, and the phenomena was called as diffraction, right? Diffraction. This diffraction pattern of electrons by crystals was similar to that observed for the X-rays, right? So what was observed for the X-rays? So the pattern which was observed for X-rays was this, right? So this was the pattern which was observed for the X-rays, and similar pattern was observed for the electrons, right? The diffraction pattern of X-rays and that of electrons are this. So this is the diffraction pattern of X-rays, and this is the diffraction pattern of electrons. The similarity of these two patterns indicate that the electrons behave like X-rays, right? This indicates that electrons behaves like a wave, right? Since X-rays have wave characters, therefore the electrons must also have a wave character, right? Moreover, the wavelengths of electrons are determined by the diffraction experiments which were found to be in agreement with the values obtained from the de Broglie's experiment, right? Right. The particle nature of matter, that is electron, had been established from a number of experiments, and its wave character was confirmed by diffraction and interference experiments. Right. The wave-like character of electron helped in making electron microscope, which is very powerful tool in modern scientific research area, because it achieves a magnification of around 15 million times. Right. So let us do the next page. Right? From this, we conclude that the electrons or subatomic particles not only have a wave-like behavior, not only have a particle-like behavior, but they also have a wave-like behavior, right? So now let us understand the significance of, although the dual nature of matter is applicable to all materials, all material objects, but it is significant for the microscopic bodies only, right? Because we know lambda is nothing but h by mp, and it is inversely proportional to the mass, right? So for large bodies, the wavelength of the associated waves are very small and cannot be measured by any of the available methods, right? So let us write this down. For microscopic or large bodies, the wavelengths of the associated waves cannot be measured by any of the available methods. Now, why is that? Because they are very small. Therefore, practically these bodies are said to have no wavelengths. Thus, any material body in motion can have wavelength, but it is measurable or significant only for microscopic bodies such as electron, proton, atom, or molecule. Right? So this may be. So we are going to show you that the wavelength of electron. Right? Let us calculate the wavelength of an electron with mass of 9.11 into 10 raised to power 6 meter per second, right? So for that, the wavelength would be h by mv, which is 6.626 10 raised to power minus 34 divided by 9.11 into 10 raised to power minus 31 multiplied by 10 raised to power 6, which comes out to be approximately 7.28 10 raised to power minus 10 meter, right? And that for on the other hand, for let us write this for microscopic, right? For microscopic particle, this is the de Broglie wavelength, and for macroscopic particle, the de Broglie wavelength is going to be, we are going to calculate, right? The wavelength associated with a ball, for example, right, with a mass of 10 gram and same velocity. Let's say the velocity is 10 raised to power 6 meter per second, right? So for that, lambda is going to h by mv, which is 6.626 10 raised to power minus 31 divided by 12, 10 into 10 raised to power minus 3 multiplied by 10 raised to power 6, which comes out to be, this implies lambda comes out to be 6.63 10 raised to power minus 38 meter. So when you compare these two things, right, this and this, we see that the wavelength for microscopic particle is way too high than for an macroscopic object, right? Hence, we say that the wave nature is dominating at the micro level, and particle nature is dominating at the macro level, right? So deviations of Bohr's. Right? So this is where we conclude for today. And in the next class, what we are going to study is the Heisenberg's uncertainty principle, right? So in this class, let us summarize what we have seen. So in this class, we have seen limitations of Bohr's model, right? Then we have seen the dual nature of particle, right? In this, we have seen that for microscopic, so we have confirmed the confirm particle nature and wave nature of electron using the Davison and German's experiments, right? Then we have also seen the de Broglie relationship. De Broglie relationship. Then we have calculated that using this de Broglie formula, that wave nature of particle of matter dominate at microscopic level, whereas particle nature of matter dominate at microscopic level, right? So this is what we have concluded, right? So here we can write Davison and Germer's experiment. So I thank you all for attending this class, and I hope you have enjoyed and learned something from it, and I hope to see you again in the next class. Thank you.